In this video tutorial, I am going to discuss the photoelectric effect. This is a very hard topic, especially we talk about it in AP chemistry. So today I'm going to give you a very simple explanation to the photoelectric effect. So first, when we start discussing the nature of light, we think that light is a wave and it has the functions and properties of waves like amplitude, frequency, wavelength. So here I'm showing you different waves with different wavelengths. You see, this is a long wavelength, this is a shorter one, and this is even a shorter one. And as you can see, when I change the length of lambda, when lambda length changes, the color changes from red to yellow to blue. So, and the length of lambda is related to the frequency of a wavelength. And when we say frequency, we also mean by this energy. So you have to keep this in mind. If I have a long wavelength, that corresponds to a low frequency light, or what means a low energy light. So this means that this wavelength over here, this figure over here, is showing me a wavelength with the lowest energy because it has the longest lambda. This one has a shorter wavelength, meaning a higher energy. And this figure over here, it has the wavelength with the highest energy because simply it has the shortest wavelength, lambda. Also, when we speak about waves and about light, we talk about amplitudes. And amplitude is how high a wave, the crest is, or how low or how high the crest is. And this is called amplitude. So if I have a wave with a low amplitude, it means that the light is dim light. But if it has a higher amplitude, a high amplitude, it means that this is a bright light. I will be discussing the effect of frequency and the effect of amplitude on the of light in the photoelectric effect. Now, of course, before I move on with this video tutorial, I would like to explain to you here why I have different colors when the frequency or when the energy of light changes. Well, light, with its wave property, it has wave, it's a wave, so it has different frequencies. So when the frequency is low, it means a low energy. The nature of waves that we call are called radio waves. A higher energy would be like microwaves, infrared, visible light. I'm increasing I'm going in this electromagnetic spectrum in this direction. So every time I'm shifting to the right, I'm talking about a higher and higher and higher energy. Like ultraviolet light, X-ray is even with higher energy, and gamma ray is a light with the highest energy. But only the portion that you see over here is the portion of light that is visible to us as human beings. And this is called, we call it the visible light. So this portion of electromagnetic spectrum, we called it visible light because only at that portion, only when the light ranges from this frequency, from these frequencies, we start seeing the color of light. And it's gonna range between a lambda, a wavelength of 750 nanometer up to 400 nanometer. Of course, we go from a low energy, 700, that's a long lambda, to a higher energy, that's a shorter lambda. So these are the colors. So this is why when we look at the examples over here, This is low frequency, color is red. Higher frequency, color is yellow. Maybe a higher one, color is blue. Now, let's go back and talk about the main objective of this video, which is the photoelectric effect. So, we said that light is a wave. Yes, but that's not the complete truth. Light has dual nature. Beside behaving like a wave, light also behaves like particles. And we say light has particle nature. How? How is that? Who discovered this? Now, I'm not going to talk history in this video. I'm just going to explain the experiment that proved that light has also another nature, which is the particle nature. So the name of the experiment is the photoelectric effect. So the photoelectric effect is the experiment that proved that light has a particle nature. Not only wave, a particle nature. Okay? Now, and what does it say? What's the outcome of this experiment? It says that metals emit electron. This is a metal. A metal emit electron, can throw out an electron when light shines upon them. Of course, a light with the proper enough energy. Okay, let's understand this properly. Einstein is the scientist who explained the photoelectric effect. Now, the photoelectric effect experiment was done years before Einstein came, but it was never explained in the proper way that Professor Albert Einstein did. So what did he explain? See, let's look at this metal over here. We are shining a light on this metal. Of course, light with the proper enough energy. And there is an electron emitted. Now, how is that a particle? I'm just going to give you a very simple example. Let's say I have a tree of apples. If I'm standing here and I'm shouting at the apples, why I'm saying shouting? Because voice is a wave, just a wave nature. If I keep on shouting on those apples, they're never gonna fall. But if I have a ball, a rock, something, a particle to hit with those apples, so let's say I have a ball and I hit this apple with this ball, the ball might result in dislodging this apple, in like making this apple fall. Now, of course, when I throw the ball towards this apple, my ball has to have enough energy to let this apple fall. So, a ball is a particle. But if the ball is a wave, it's never gonna let the apple fall. And that's the conclusion that Albert Einstein did. So if light is only a wave, it's never gonna eject an electron. But if light has a particle nature, hitting an electron with particle is gonna result in moving this electron from its place. Now, let's explain this and go into further details. So, look at this atom with electrons. This wave here represents the light. Now, light, and Einstein explained that he said that light energy must come in packets, which he called photons. Photons are the particles. So I'm just going to draw dots, and I'm gonna call these dots packets or photons. So a light is composed of packets. The light comes in packets. These packets are the particles. These packets are the photons. So if this photon is coming toward the electron, remember, it's a particle nature. It's coming toward this electron. If this photon has the right energy, it's going to move the proton from its place. We say dislodge the electron. Now let's look at this graph over here. What does it say? Look at this line over here. We are shining light on a metal, but this metal, there are no electrons emitted, simply because this light did not meet the required energy. We call it the threshold frequency. There's a minimum amount of energy. We need to overcome it in order to dislodge an electron. Electron, let's say this in a clearer way. Electron is attached to a metal with a binding energy. To dislodge it, the photon has to meet this energy or be higher than that energy. So here we did not meet the minimum required energy to dislodge an electron. But once we reach this amount of frequency, you can see that electrons are started to be emitted. Okay? Now, whether the light is going to be with low intensity, like dim light, less electrons are ejected, or if it is with high intensity, high amplitude, more electrons are dislodged. So we need a minimum requirement of energy to dislodge the electron. Now, let's just look at these figures over here. Here I have a light with different frequencies, different energies. This is the lowest energy. Obviously, no electrons are dislodged because we did not meet the minimum required energy. We did not overcome or equal to the binding energy. The second one, if you notice here, the lambda is shorter compared to the red one, meaning higher energy than the previous one. Here, we met the threshold energy, the threshold frequency. An electron is dislodged, but not too far from the metal because probably the energy is not very high. But if we increase the energy, an electron is dislodged, is emitted from the metal with also a higher kinetic energy. I'm going to explain this using the FET Colorado simulation. Now, let's look at another example. Let's say here, this is the light emitted through the metal. But the energy of this light is not enough. We did not meet the threshold frequency. Therefore, no electrons emitted. This one, we have a higher energy. The light is coming with a higher energy. So we dislodge the electron with a certain, electron is traveling with a certain kinetic energy. Whatever energy is remaining, whatever excess energy remaining after dislodging the electron, it goes to the kinetic energy of that ejected electron. So of course, a light with the highest energy is going to dislodge the electron from its place, but the traveling electron is going to go with a higher remaining kinetic energy. Now, one last thing, because I still want to explain the effect of amplitude. The effect of amplitude. When I say amplitude, and I mean by this the intensity of light. And this is the best example given. Whether I'm shining one torch or two torches toward a metal, if we did not meet the minimum threshold frequency, whether you light one, you direct one torch or two or 20, no electrons are going to be ejected because we did not meet the minimum required energy. Now, this figure over here and this figure over here, obviously, the light directed toward the metal meet the minimum required energy. That's why you see here ejected electrons. Now, of course, if I direct more light, so this is dim light, This is a bright light. This one with a low amplitude. Amplitude meaning low intensity. Low intensity. I have electrons ejected, but less. Now let's look at the brighter light. Brighter light means a higher amplitude. And the higher amplitude means a higher light intensity. So, again, I still have electrons leaving the metal with the same kinetic energy, but here more electrons are ejected. Now, I'm going to take you to the FET Colorado simulation. I will be providing a link to this simulation in my description for the video. So let's look at this one. This is the photoelectric effect experiment. Let me choose copper metal, just any metal. Here, over here, I have the intensity and I have the nanometer. So I'm going to play with the intensity of light, whether I have a dim light or I'm going to change it with a brighter light. And down here, I'm going to play with the energy of the light. So let's start with the lowest energy. Now, lowest energy, as you can see, no electrons are yet emitted because simply we don't have enough energy. So whether the intensity was low, amplitude is low, or high amplitude, still we did not meet the threshold frequency and no electrons are emitted. Now let's start increasing the energy. And as you can see, the lambda, the wavelength, is getting shorter. I'm increasing the energy of the emitted light, energy of the light, directed toward the metal. But still, whether the intensity is low or the intensity is high, no electrons are ejected. We did not meet yet the threshold frequency. Let's increase more and more and more the energy of the light. And when I'm increasing the energy of the light, you can see that the color of the light is changing. So again, whether the intensity is low, which means low amplitude, or high amplitude, nothing is changing simply because we did not meet the threshold. So imagine I'm throwing a ping pong ball toward a glass window. It's not going to break it. But if I throw a baseball toward a window made of glass, probably it's going to break it because it has a higher energy. Now I'm going to start increasing slowly the energy of this emitter, of this light directed toward the metal. Still nothing. Now I want to keep the intensity low to show you the effect of intensity. Again, I'm going to increase more and more and more the energy of the light. Still, I don't have electrons dislodged. I keep on increasing. Nothing. Oh, here we go. Let me go back. You see, the first electron dislodged was coming out at a slow energy. It means that we finally met the minimum required energy to dislodge an electron. Okay? Now, as you can see, the electrons ejected from the surface of this metal are coming out with a low kinetic energy. You see, they're not very high. Now, let's increase the intensity. By increasing the intensity, the speed of the ejected electrons did not change, only their number now is more. Okay, now let's go back to a low intensity and give you a higher and higher and higher light. So what's happening here? The ejected electrons are leaving the surface of the metal with a higher kinetic energy because now the remaining energy after the binding energy is higher and all of it goes to the kinetic energy of the electron. Now whether I increase, now if I go and choose the option of higher intensity, I see more electrons ejected from the surface of this metal, but all of them still at the same kinetic energy, at the same speed. If you have questions about the photoelectric effect, please write them in your comments. I'll be answering them, and always follow with my channel to see more videos about the photoelectric effect and topics related to AP chemistry.